Diffusion weighted imaging. Go ahead and pause the video here and answer these questions. I'll go over the answers after I finish discussing diffusion weighted imaging. Diffusion weighted imaging is the best MRI sequence to diagnose an acute stroke. Typically, acute stroke is arterial in origin, and so that's going to deprive cells of oxygen. When we deprive cells of oxygen, they can't do oxidative phosphorylation and produce sufficient ATP to power their sodium-potassium ATPases. Normally, the sodium-potassium ATPase is going to pump 3 sodium outside of the cell and 2 potassium into the cell. You have these aquaporin channels, which allow free movement of water in and out of the cell. So since there's more ions outside of the cell, water is going to follow those ions. That's the principle of osmosis. And we're going to have more water in the extracellular space where there's plenty of room to move around, plenty of room to diffuse, no restricted diffusion, free diffusion. When there's cytotoxic edema, an acute stroke, we have failure of the sodium-potassium ATPase. And as a result, we have 3 sodium ions trapped inside the cell for every 2 potassium ions that are trapped outside of the cell. So net more ions inside of the cell, water is then going to move into the cell and cause cellular swelling, cytotoxic edema. Because there's less room to move around inside the cell because of the organelles and whatnot, there's restricted diffusion of those water molecules once they're intracellular. So acute stroke is not the only clinical context in which we have a higher proportion of water that's in the intracellular space. We also can see that with round blue cell tumors like lymphoma or medulloblastoma that are relatively cellular. We can also see restricted diffusion in the setting of an abscess, and that's not due to intact cells with water rushing into the cells or just a higher percentage of cells relative to non-cellular water. It's due to the water being immersed in this viscous substance that is pus. And we can see that whether it's intraparenchymal, an abscess, whether it's in the subdural space, a subdural empyema, or in the subarachnoid space, a meningitis, or in the ventricles, a ventriculitis. It doesn't really matter. As long as there's pus, the water is not going to be able to move around as freely, and that's going to restrict diffusion. So how does diffusion-weighted imaging work? The essence of diffusion-weighted imaging is the application of a bipolar gradient magnetic field. So this is the first time we're talking about gradient magnetic fields, so I'm going to try to introduce you to that concept. So consider a sagittal image that consists of 5 voxels. A voxel is just a pixel with an associated volume. Okay, this is the fundamental unit of any MR image. So if the MRI system is well calibrated, let's assume we're dealing with a 1.5 Tesla machine, each of these voxels is going to experience a magnetic field strength of 1.5 Tesla. Now let's apply a gradient magnetic field along the z-axis, the long axis of the patient. So how is that going to affect the magnetism in the different voxels? Well, what's going to happen is that at isocenter, basically in the center of the gradient, the magnetic environment is not going to change at all. It's designed that way. So it's going to be 1.5 Tesla still in the middle, but when we get to the more inferior slices, the gradient is essentially going to subtract from the main magnetic field, so it's going to experience a lower magnetic field strength. Let's just arbitrarily say 1.3 Tesla. Whereas more superiorly, it's going to add to the baseline B0, and it's going to experience a stronger magnetic field strength. Let's arbitrarily say 1.7 Tesla. Okay, so each voxel is now experiencing a different magnetic field strength. Notice how that even within the same voxel, different columns within that voxel are going to experience different magnetic field strengths. So we're arbitrarily going to divide the voxel into 2 columns. You could divide it into any number of columns, but just for simplicity, we're just going to think of a voxel being divided into 2 columns. So when we apply this gradient magnetic field, the left-hand column is going to experience a lower magnetic field strength than the right-hand column. So what? Well, remember, the rate at which hydrogen nuclei precess is determined by the magnetic environment that it's experiencing, which is mainly due to the applied magnetic field. So what's going to happen is that the hydrogen nuclei in the left-hand column are going to precess more slowly compared to the right-hand column. So the left-hand column, they only make a quarter turn, and the right-hand column makes half of a turn, while this first lobe of the uh, bipolar gradient magnetic field is turned on, the plus GZ. So this is going to result in loss of phase coherence. Why do we have loss of phase coherence? Well, anytime we have spins that are pointing at different positions along the clock face, we're losing phase coherence. And remember, when we lose phase coherence, we lose signal. So this is that diagram that I keep referring to from Alan Elster, and it's just showing that as we lose phase coherence, as the individual spins point to different positions on the clock face, their transverse components are going to start canceling with each other, and the overall strength of the transverse magnetization, the signal we're trying to sample, is going to get smaller. Okay? So far, all we've done is destroy a signal by applying this gradient magnetic field. Okay, so let's assume that these spins remain within the columns because there's restricted diffusion, either because there's an infarct, or it's a lymphoma, or it's an abscess or pus, whatever. It's staying within the columns, restricted diffusion. So now we're going to apply the gradient magnetic field in the opposite direction, same magnitude. So let's see what happens. So the spins at the previous gradient caused to precess slowly, so that was in the left-hand column, are going to now precess more quickly. So they're going to make a half turn. The spins that the previous gradient caused to precess quickly are going to now precess slowly. So they only make a quarter turn. Now look, they're back in phase with each other. So when we turn off the gradient magnetic field, both columns are going to experience 1.5 Tesla effectively, and they're going to preset this at the same frequency in phase with each other. So restricted diffusion in a bipolar gradient magnetic field results in preservation of phase coherence and therefore signal. Now let's assume the spins do not remain within the same columns due to free diffusion, okay? So the spins are moving into the opposite column. So let's see what happens now when we apply the second lobe of the bipolar gradient magnetic field, the gradient magnetic field in the opposite direction. So the spins that the previous gradient caused to precess slowly, so those were these spins, are going to continue to precess slowly. The spins that the previous gradient caused to precess quickly are going to continue to precess quickly. So look what's happened. We've essentially completely destroyed the phase coherence. We've worsened the phase coherence. There's no phase coherence now. So when we turn off the gradient magnetic field and the spins go back to precessing at the same rate, the lower more frequency, remember, 64 megahertz in a 1.5 Tesla environment, they're going to preset this at the same frequency but out of phase with each other. So as a result of that loss of phase coherence, there's going to be destruction of signal, right? We need phase coherence to have signal. So free diffusion results in loss of signal in the face of a bipolar gradient magnetic field, which is the core of diffusion-weighted imaging. Now we understand how a bipolar gradient magnetic field can induce diffusion contrast into our image. Free diffusion is going to appear black. Restricted diffusion is going to appear white. The problem is that you can also have white signal on a diffusion-weighted image from tissues that have a long T2. So let's discuss that briefly. The reason is because diffusion-weighted imaging is a T2-based technique. So what does that mean? That means that it has a long echo time. Remember, T2 star contrast comes from a long echo time, the time between the 90 and when we sample our signal at TE. So T2 weighted imaging comes from a long echo time and a spin echo, a 180-degree radiofrequency pulse positioned halfway between the 90 and TE. So the diffusion-weighted image pulse sequence is typically constructed that way. The effective TE is long, and there typically is a 180-degree radiofrequency pulse positioned halfway between the 90 and that effective TE. So that means that if we have tissues that have a very long T2, they're going to also potentially appear bright on the diffusion-weighted image. So we need to figure out some way to tell that apart. So what we do is we acquire another sequence, another set of images called the B0, which is identical to the diffusion-weighted image sequence, except we leave out the bipolar gradient magnetic fields. We leave out the diffusion weighting. So bright signal on a B0 image is only going to be reflective of tissues with a long T2, and obviously a proton density. But that's true for any image. Proton density comes into play in every image we look at. But anyways, okay, so let's talk about the ADC now. So if there is minimal loss of signal from B0 to DWY, that's going to be represented as dark intensity on an apparent diffusion coefficient image. And that's what we see in restricted diffusion. If we have a large loss of signal from B0 to DWI, so that means the bipolar gradient magnetic fields cause a ton of dephasing, then we're going to see white intensity on an ADC. So that's going to reflect long T2 or T2 shine through. So ADC is a post-processed set of images that compares B0 to DWI quantitatively. So there we go. So in this example, because the ADC is black, that means there was minimal loss of signal from B0 to DWI, and there's true restricted diffusion. Okay, so why is that the case? Why would we have minimal loss of signal from B0 to DWI if there's restricted diffusion? So we already understand this, right? Let's review. So when we apply the bipolar gradient magnetic field, the first lobe of it, we're going to cause dephasing. The left column spins are going to precess more slowly. The right column spins are going to precess more quickly. As long as they stay within their columns, which they will because there's restricted diffusion, when we apply the second lobe of the bipolar gradient magnetic field, which has the opposite direction but same magnitude as the first lobe, we're going to take those spins that were previously precessing slowly and make them precess more quickly. The ones that were precessing more quickly, we make them precess more slowly. So essentially they catch up to each other. They go back in phase at the end of this bipolar gradient magnetic field when there is restricted diffusion. So when there's restricted diffusion, there's minimal loss of signal from B0 to DWI because we've preserved the phase coherence from those spins on the diffusion weighted image. Let's consider this case. So we know that when we see white signal on a diffusion weighted image, it doesn't have to represent restricted diffusion. It could also represent tissues that have a long T2, aka T2 shine through. So to tell them apart, we have to acquire another set of images, the B0, which is the same as DWI, except we just leave out the bipolar gradient magnetic fields. If there's minimal loss of signal from B0 to DWI, that's going to be black on the ADC image, and that represents restricted diffusion, like we saw in the last case. If there's a large loss of signal from B0 to DWI, this is represented as white intensity on the ADC, and this is what we see in the setting of long T2 or T2 shine through. Again, ADC, apparent diffusion coefficient, is a post-process set of images that quantitatively compares B0 to DWI. So here it is. So in this case, the ADC signal is white, so that tells us that we're dealing with tissues that have a long T2. There's no restricted diffusion here. So why do we need the ADC? Why can't we just visually compare? We can look at B0, look at DWI, and be like, I don't think there's a large loss of signal, so, probably restricted diffusion. Why can't we do that? Well, this is a perfect example of how it fails. So if we look at the last case, I would argue it's pretty similar in appearance to this current case I'm showing you. So on the DWI image, we have light bulb bright signal. On the B0 image, we have sort of faint white signal. And so, you'd expect the ADC to be the same in both cases, but they're opposite. So our eyes can fail us. That's why we need to have a quantitative comparison. Bottom line, if your study doesn't have an ADC set of images, remind your MR technologist to send it. You really shouldn't be interpreting the study until they send it. So this was a case of T2 shine through. This was actually an MS plaque. This was not an infarct. This was an infarct. So why is T2 shine through associated with a large loss of signal from B0 to DWI? Well, we understand this. Dephasing is going to result from the first application of the gradient magnetic field. When water protons diffuse across columns, look what happens. More dephasing is going to result when we apply the second lobe of the bipolar gradient magnetic field in the opposite direction. So the spins that were precessing more slowly, because they switch columns, they're going to continue to precess more slowly. The spins that were precessing more quickly because they switch columns, are going to continue to precess more quickly. So as a result, we have worsened the phase coherence. There's even more loss of phase coherence with the second lobe of the gradient magnetic field. As a result of this loss of phase coherence, we're going to lose signal. So when you go from B0 to DWY, when there's free diffusion, there's going to be a large loss of signal. And another way to think about this is that the ADC, if you see white intensity there, that means that there is free diffusion. If there is black, that means that there is restricted diffusion. So in other words, it's a direct correlate for diffusion. If it's white, there's a lot of diffusion. If there's black, there's restricted diffusion.